All right, so for these next set of questions, this is what we're given. In a completely randomized design, 11 subjects were assigned to each of the 5 treatments of factor. Below is a partially completed ANOVA table. So what we need to do is we need to figure out what kind of ANOVA this is, single factor, 2-factor with replication, 2-factor without replication. Then we need to fill out these blanks. And then once we do that, we can start looking at the questions and answers. All right, so what kind of ANOVA do we have? What I'm going to do is switch over to the cheat sheet, and an easy way to figure this out is to see what does this table match with. So let's look at this single factor, right? This is a single factor ANOVA. You can see that we have treatments, error, and total. Here we have treatments, error, and total. So I can tell that this is going to be a single factor ANOVA because these match up with these. If we were to just check, let's say we were to first check our 2-factor without replication, you can see that here we have blocks, treatments, error, total. Here we don't have blocks, right? We don't have blocks, treatment, error, total. We just have treatment, error, total. So it can't be this one. And let's just go down here. This says factor A, so sample, columns, factor B, interaction. Like you don't see interaction here. You don't see 2 factors. So this is not going to be it either. All right. So now that we have established that we have a single factor ANOVA, we can start to fill out this table. Okay. So let's figure out what our degrees of freedom are. So how do we get our degrees of freedom for treatments? You can see it's going to be K minus 1. But what's our K? So K is going to be 5, right? 5 treatments. So we're going to do 5 minus 1 to give us our degrees of freedom for treatments. So 5 minus 1. Okay. Now we need the degrees of freedom for error. Let's go back to our cheat sheet. What's the degrees of freedom for error? N of t minus k. You know what? That's kind of a more complicated formula than this one right here. So I'm going to skip this one for now and just go to the total because that's not too bad. That's just n of t minus 1. N of t are the 2 numbers that are given to us in the problem multiplied by each other. Or you can say it's the total number of observations. The way that we calculate that is by multiplying the 2 numbers that are given to us. So in here we have 11 and 5. So we're going to be multiplying 11 by 5 to get our n of t. Then we need to subtract 1. So what is 11 times 5? That's going to be 55. And then we need to subtract 1 for our degrees of freedom. So 55 minus 1. Okay, now to get our error, we can do our n of t minus k. So that's going to be 55, right? We said n of t, 11 times 5 is 55. Let's just do this. N of t is 11 times 5. Okay. And we said our k was 5. So I'm just writing out what we already talked about. Okay. So then n of t minus k is going to give us our error. So n of t minus k, that's going to be 55. Right? Minus 5, so 50. Another way that you can do this, let's say you're like, this is kind of complicated. I don't really know how to get this, or I don't want to do this one. There's a way around it. What you can do is just take this total and subtract it by this treatments, because these 2 values added together is going to give you your total. So you can take your total and subtract the degrees of freedom for treatments, and that's going to give you your error. All right, now let's do the sum of squares. This value we can get by subtracting this from this again, because this number right here is going to be these 2 values added together. So this minus this. There we go. Now we need to get our mean square for treatments and mean squared error. So how do we get that? Right here, you can see our mean squared for treatments is our sum of squares for treatments divided by our degrees of freedom. So that's going to be the sum of squares of treatments divided by our degrees of freedom. So this value divided by this value. There we go. to get our mean squared error, it says sum of square error divided by our degrees of freedom, and t minus k, that's our degrees of freedom. So I'm gonna take this value. It seems like this is 2 cells, so I'm just gonna do 320 divided by 50. Okay. So 6.4. I just use cell referencing. Okay, there we go. So this is just 320 divided by 50. Okay. Now let's get our F test statistic. So that's our mean squared for treatments divided by mean squared for error. So that's just going to be this value divided by this value. There we go. We need to get our p-value as well. So what's our p-value? You can see that right here. It's that f.dis.right. So f.dis.right. Whenever we are filling out the Anova table for our p-value, it's always going to be f.dis.right. Always. Okay. So our x is the F test statistic. Okay. Our degrees of freedom 1, that's going to be the degrees of freedom for our treatment. So it's this one. Then our degrees of freedom 2 is going to be the degrees of freedom for error. So this one. All right. There we go. And if you guys recall, whenever you have this e to the negative whatever, that means you have to go back many decimal places. So that means this p-value is going to be close to 0. All right. Now that we've filled out the table, we can start looking at the questions. So number 8 says, what is the null hypothesis implied in this problem? The null hypothesis has to have equals in it. So we can see that both of our answer choices have equals in it. So that's great. But whenever we're doing Anova, we're testing on the treatments. So how many treatments do we have? 5. Says that right here in the problem. So that means we're going to have mu1 equals mu2 equals mu3 equals mu4 equals mu5. So that would be our answer choice. Okay. So number 9 says, what is the mean squared for treatments? Mean squared for treatments. So 215. Number 10, what is the value of the F statistic? F test statistic, it's 33.59. That matches with this answer choice. What is the p-value? P-value, remember we said that this number is very close to 0. So we're just going to say it's 0. And at 1% level of significance, do we reject or do not reject? So what's our alpha? Our alpha is 0.01, right? What's our p-value? Our p-value is close to 0. So I say 0. Because our p-value is less than alpha, that means we reject. So that would be our answer.